Hi, my name is Raman Sharma and I'm a program manager with the Visual C++ team. In this session, I'm going to talk about building C++ universal apps for Windows 10 using Visual Studio 2015. So this is roughly the agenda for today. I'm going to provide a brief overview of some of the new concepts that Windows 10 introduces for app developers. We're going to dig deeper into this new concept called Universal App Platform. We'll take a look at how C++ interacts with some of these new concepts that the platform introduces. And we'll talk about some of the cross-platform features that C++ introduces to help you build apps for more than one platform. And then we'll take a look at a demo of some of these new features in action. So it's not very surprising to see that the convergence of the various Windows platforms is a big theme for Windows 10. We've been on this journey for a while now. Over the past few Windows releases, we have seen the operating system kernels for devices like Xbox, PC, and phone getting converged. In 8.1, we saw the programming model for Windows apps and Windows Phone apps getting converged. And Windows 10 takes this journey a step further, and it now enables a single unified developer experience that allows you to create a single app that can run on multiple devices, which is what we are calling the One Windows platform. You can now create a single set of binaries, bundle them into a single app package, upload them to a single app store, and still make them available to your end users on multiple devices, on a wide variety of devices. And even when your app runs on these wide variety of devices, Windows 10 enables you to provide a great, rich, and very device-appropriate experience, irrespective of what device the app is running on. And you can do all of this using a single SDK and a single set of tools from Visual Studio 2015. So one of the most important concepts that Windows 10 exposes to app developers is this thing called Universal App Platform. This is what really allows you to build a single app that can run on multiple devices. Before we understand Universal App Platform, we need to understand some of the building blocks that build it. So the first building block is this notion of API contracts. So an API contract is nothing but a bundle of operating system functionality exposed as APIs. Instead of relying on a specific API, your app relies on an API contract. A platform is nothing but a bundle of API contracts. So if your app targets a platform, the app can rest assured that all the specified API contracts would always be available on all target devices that claim to support this platform. And once we know what a platform is, UAP or Universal Application Platform is nothing but the most common platform, which consists of the most common, most popular, and the most fundamental API contracts that are always available on all devices, and your app can always rely on them. Windows 10 also has ambitious goals in terms of being able to provide newer functionality at a much faster cadence, both to the end users as well as the app developers. So this requires a solid versioning story. And the way Windows 10 handles this is by creating an alignment between a version of a platform and the versions of the underlying API contracts. So you can understand this alignment simply by opening up this file called platform.xml, which ships inside the Windows 10 SDK. If you look at this file, it says that this platform, which is called UAP, with this specific version, actually consists of these three API contracts with these specific versions. Now, API contracts can change independently of each other. What this means is that a future version of this UAP platform might consist of the same versions of two of these API contracts, but a newer version of the third API contract. So what this allows you as a developer is an ability to target a well-defined concept called UAP instead of having to worry about ever-changing operating system versions. And it also allows you to create a single app that you can write once and run everywhere on multiple devices and also on multiple versions of the platform. So Windows 10 allows you to write adaptive code, which does the most device-appropriate thing on every device. And the way Windows 10 handles this is by providing device-specific extension SDKs, which are nothing but a bundle of are device-specific API contracts. So we have extension SDKs for mobile apps. We have extension SDKs for desktop apps. For a mobile app, you might want to make a phone call, the functionality which is specific to a mobile app. Or for a desktop app, you might want to connect a USB printer, which not many mobile devices can do today. So once you have done that, from a developer perspective, the experience is as simple as referencing this platform extension SDK from inside your UAP app projects, and then Visual Studio automatically understands all the things that a platform extension SDK exposes and makes all the build time artifacts like headers, libs, and metadata available to the project at build time. In addition to this, Windows 10 also introduces this new concept of runtime API checks, using which your app can figure out what the device is capable of at runtime before calling any API. So this is a simple C++ code example which shows you how you can use this API called API information to figure out whether a type called hardware buttons is present on the target device or not. And if this type is indeed present, then you can go ahead and add an event handler to the camera pressed event of the class. So what this allows you is an ability to create a single binary per architecture. This binary not only runs on various devices, but on multiple versions of the platform. If you've built any C++ apps, you must realize that Visual C++ libraries form an important part of the C++ developer experience. In VS 2013, we had two different runtime library packages for Windows Store apps and Windows Phone apps. In VS 2015, we have a single universal package that fulfills the runtime dependencies of all universal apps. It contains a set of binaries that run on all devices. So not only this introduces great improvements in deployment, but it also provides a great proof of concept about being able to create a single set of binary on this platform which can run on multiple devices. The C runtime, which has been a part of Visual C++ libraries for long, is now actually a part of the Windows 10 operating system itself. So this library will ship inside the operating system, which means that you will not see newer versions of the CRT with successive releases of Visual Studio. You can still use new releases of Visual Studio and still rely on the fact that the C runtime is always in the operating system. In case of the C runtime library, it is used not only by universal apps, but also by classic desktop apps and some operating system components as well. Again, this introduces much simplicity of deployment. It provides disk space usage gains in the sense that there are fewer CRT DLLs floating around. And it also provides performance benefits because you have fewer runtime DLLs loaded inside your process at any time. This is, of course, a first step towards our eventual goal of arriving at a stage when we have a set of binary stable Visual C++ libraries which can be freely used by even future versions of the compiler toolset. Now, being able to create a single binary is great, but these days users use their apps on multiple devices, and they not only expect the apps to work, but they expect the apps to work great. They expect the apps to provide the richest, most device-appropriate experience based on whatever the target device form factor is. So if your app, while running on a PC or a tablet, is just a magnified version of how it looks like on phone, then you are probably missing a trick. Now in this area also, Windows 10 provides great affordances, such as custom visual state triggers, which allow your app UI to adapt based on changes such as screen orientation and size, etc. So this is a simple example of some XAML code that changes the orientation of a panel from vertical to horizontal if the minimum window width exceeds a particular threshold. In addition to this, Windows 10 also provides some built-in controls which are automatically adaptive, and they do the right thing depending on the target operating environment. So we realize that Windows is not the only platform you build your apps for. There are other popular platforms as well. And we also realize that C++ by design is a cross-platform language. So we want to help you build your C++ apps cross-platform, irrespective of whatever platform you're targeting. And we have done a bunch of things in that area as well. The first and the most important thing is adding a number of language and libraries conformance features to our compilers and libraries. We've done a lot of work to implement major pieces of C++11 and C++14 standards. This allows you as an app developer to write cross-platform code that can build not only using Visual C++, but using other standard compliant compilers as well for other platforms. And this also expands the list of open source C++ libraries, which are very popular on other platforms like iOS and Android, and can now be easily used for Windows apps as well using Visual Studio 2015. VS now provides native support for building C++ Android apps. We have done this by integrating open source toolsets like Clang LLVM into Visual Studio itself. And in keeping with the spirit of being cross-platform, we've done a lot of work to allow you to manage your cross-platform C++ code base, which can be shared in multiple mobile platform apps. There's a separate session that goes into much more detail on this specific topic, if you're interested in that. And that brings us to the demo. So let us jump into the demo and look at the product in action.
One thing you need to know about building Windows 10 apps is that developer tooling for these apps is an optional install feature in Visual Studio. You have to remember to select that as an option while installing VS. Once you select that option, you get the right tools for all languages like C++, C#, and JavaScript. Anyway, here I have Visual Studio 2015 running on a Windows 10 machine. I've already installed all the required tools. So let's go ahead and create a universal C++ app. If you go to File, New, Project, under Visual C++, Windows Universal, you'll see a bunch of project templates like XAML, DirectX, DLL, Static Library, Windows Runtime, and so on. For now, I'll just select a blank XAML app and hit OK. Now that the project has been created inside the IDE, let's take a look at some Windows 10 specific things in your project structure. If you look in the Solution Explorer, under the References node, you will notice these API contracts. These contracts are a part of the Universal App Platform, so they are always added to all Universal projects created by VS. At build time, these contracts, which are just Windows metadata files, are passed along to the C++ compiler, which understands these contract WinMDs and therefore allows you to call any API defined in them. You'll also notice that although this is a universal project, it doesn't have anything called shared code. And that's because if your app is relying only on the API contracts contained inside the UAP, then all the code inside your app is shared code, and it can always run on all devices without requiring to build separate binaries for desktop and phone. And if you want to see evidence of that, you can open up this file called package.apex manifest. This file basically determines the target of your application package, and in the dependencies section, you can see that your app targets a device family called Windows Universal, which means that it can run on Xbox, desktop, and phone. Okay, let's close these files now, and moving on, let's write some simple XAML code. I will open the main-page.xaml file in the XAML editor, and we'll write some simple XAML code, and we'll see how the code looks like on both the local machine and inside a mobile emulator. So the code I'm going to write is really simple. I'll just create a text block and give it some nice text like hello Windows 10, and I'll position it in the center of the window and give it a nice font and close it out. So let's hit F5 to just build and run this app on the local machine first. So you see the app loaded here, nothing too surprising here. As expected, the text appears in the center of the window. The only new thing is that this is not a full screen app, which is a new thing for Windows 10 Universal Apps running on desktop. So let's close this app for now. And now, instead of running the app on the local machine, let us launch the app on a mobile emulator. So one thing you should notice here is that Visual Studio did not need to build the app again. It is just using the same set of binaries and deploying them onto the mobile emulator. Now this is how the app looks like on an emulator. As you can see, the text still appears in the center, and this is in fact a full screen app, which is what makes sense for a mobile device without a keyboard and a mouse. So this is great, but what if my app has a scenario where it wants to do something specific while running on a phone device? So let's go ahead and close this app and look at that scenario. In that case, the first thing you want to do is add a reference to this thing called the Microsoft Mobile Extension SDK and hit OK. As you can notice, by doing this, Visual Studio pulls in all the phone-specific API contracts contained inside this SDK, and they are made available to the compiler at build time. So now we can go ahead and make phone-specific API calls. But I still want to make sure that my app continues to do the right thing for desktop. To enable that scenario, I can use the Windows 10 runtime API detection, using which an app can figure out the capability of a device at runtime. So let's open up the mainpage.xaml.cpp file. And in the constructor of the main page, we'll write some code. I'm calling the new API information API provided by Windows 10 to figure out whether a type is present or not. And the type I'm looking for is a type called hardware buttons. And depending on whether hardware buttons are present or not, my app can determine whether this is a mobile device or not. And if the hardware buttons are indeed present, I'll go ahead and add an event handler. To the camera pressed event. And adding an event handler using the IDE is actually really simple. You just need to hit tab twice, and it actually goes ahead and creates a dummy implementation for you. I don't want this dummy implementation, so I'll delete this code and just simply pop up a message dialog every time the button is clicked. Create the dialog, and I'll just go ahead and show the dialog. Let's run this app now by hitting F5. So it's still the same app, but when I click on the camera button inside the mobile emulator, you'll see that the message dialog pops up. If I close this app and run it again on the local machine, you'll see that there is no change and the app continues to run as it used to earlier. So let's go ahead and close Visual Studio here. So that was a simple example of a universal C++ app. Let us now take a look at a slightly more complex example. Here I have this solution with two projects. One is a C++ XAML project called FaceFinder, and the second is a C++ Windows runtime component called WinRT FaceDetect. As you can guess from the name, this app will have something to do with detecting faces in pictures. The XAML app references the WinRT component, and the WinRT component references something called an OpenCV SDK. So this is basically the cross-platform C++ image processing library called OpenCV, built using Visual C++ 2015 and neatly packaged into an extension SDK, which can be easily used in any universal project. In this case, the WinRT component simply uses the OpenCV API to perform face detection on a set of pictures. Let's look at the UI of the app. As you can see, the UI of the app is a very simple XAML with a stack panel that has two grid views, both of which display some images using XAML data binding. Now, one to display the pictures and the other to display the detected faces. Let us go ahead and run the app on the local machine and see what it looks like. So here's the app. Let us hit the first button to load the images, which brings up this dialog, and I can select all the images in this dialog and hit open, and all the images are displayed in a nice grid view in my window. And I can hit the second button now to detect faces, and as you can see, the faces are being detected and asynchronously displayed inside the grid view. If I resize this app window, you'll notice that there is already some amount of adaptiveness in the UI. The grid views automatically relay out when the window's size changes. However, after a certain point, it falls apart, and at a very narrow window size, we can hardly see the bottom grid view. We'll look into this problem later. For now, let us just close this app. And instead of launching it on the local machine, let us launch it in the mobile emulator. So we have the same app actually launching inside the emulator, and when I try to load the images, I don't see anything here because all the pictures that were present on my desktop are not really present on the mobile emulator. This means that in case of a phone, the app will have to figure out a different way of loading the images. This is the second problem we'll need to look into. So let's close it. Let us go back to the main page.xaml and see what happens when you click the load button. We have this event handler called load button click. I can easily go to the definition of this function just by selecting go definition. And this brings me to this event handler called load button underscore click. And we can see that it uses the file open picker API to load a set of images. And then it has some internal logic to display those images in the grid view inside my XAML. However, we know that there are no images on the phone emulator, so instead of loading the images from there, we will load them from within the app itself. Now, I've already added all the images to this folder called people inside my app project. All I need to do now is to load it from within my app at runtime. So in order to do that, I'll go ahead and uncomment this code. What this code does, it checks for the presence of a type called hardware buttons, and based on which it determines that the app is actually running on a mobile device. And in that case, it goes to the installed location of the app, looks for a folder called people, and loads all the images from that folder. Now, it doesn't actually do anything after that. What needs to happen here is just to display the images. That code already exists in the below portion here. And instead of duplicating it, I will go ahead and use the new ID refactoring feature called extract method to create a separate method out of it. I'll give it a name called display selected files. And once this implementation has been created, I'll copy this API call and paste it in this code that I've just created as well. but I still want to make sure that my app continues to do the right thing when it is running on non-mobile devices like desktop. So in order to do that, I will put this bottom block into an else section. Okay, so we have one problem solved. Let us now look at the problem of the incorrect UI layout. So I'll go back to the main page.xaml. So we can see that here is a stack panel which contains two grid views which are vertically stacked. So what I need to do now is uncomment this simple XAML code. This XAML code creates a custom visual state trigger that dynamically changes the orientation and a few other properties based on the width of the window. So I'll save this file and just hit F5. So the app loads. Now when I click the load button, I can see the images getting loaded from within the app itself. And when I click the detect button, I'll see that the faces are also getting populated in the grid view right next to the initial grid view. So let's close this app now and again run it on the local machine. Even in case of a local machine, you'll notice that the app actually did not have to be rebuilt. The same binaries actually got deployed to the local machine now, and they continue to run just fine. I can again select all the images from here, hit open, and hit detect faces. And notice that my app is still fluid, but after a certain threshold, my custom visual trigger logic takes over and it displays the two grid views side by side rather than on top of each other.
So that was a brief overview of building C++ universal apps using Visual Studio 2015. If you're interested in learning more, here are some resources. The VC++ blog provides information about all the work that C++ team does, and we have blogs for Windows developer experience as well. We hope you like these features, and we are looking forward to your feedback. Thanks for watching.